Okay. Hello, everyone. This is Shariar. So this is our Qiskit Fall Fest event, and as we promised, we will be having experts on quantum computing. And this year, uh, where we have like the quantum mechanics actually got a Nobel in physics. So that's so much interesting things that's happening in quantum computing. Okay, so we will start our session today. We have a special guest with us from IBM, who is Raghav. So Raghav will obviously introduce you guys with quantum computing in Qiskit. So I won't be describing much more about what Qiskit is and what quantum computing is. So without any further ado, let's add Raghav to the stream. Hello, Raghav. Can you hear me?
Yeah, thanks for having Shariar. Yeah,
Yeah,
nice
thank you
to
so
meet
much, Raghav, for giving time for our community, for the community growth. So it would be great if you can just introduce yourself and then we can move with the stream.
So myself, Raghav, I am a application developer at IBM Consulting
Mhm.
and a Qiskit volunteer advocate. So I volunteer to increase quantum community in research or study, education, and others. So feel free to reach for any quantum events or something you want to learn about. Yeah.
Yeah, great, great. So yeah, it just basically aligns with our community event, right? Okay, let's then start our stream. And okay, we have just added the slides. Let's start.
Hundreds years ago, in 1925, Heisenberg first published uncertainty principle to honor that United Nations has decided to celebrate 2025 as International Year for Quantum. Before moving forward, I want all of you to just spend some time on this picture. Yeah, you can see many good thinkers like R.P. Feynman. So this picture was captured in 1981 at MIT Edicott by Charles Bennett. These 50 thinkers engaged and discussed physics about computing. In 1925, Heisenberg started first quantum revolution. This is the glimpses of second quantum revolution. And here only our favorite Feynman gave idea that nature is quantum and you need a computer that follows closely quantum principles to simulate it. So now, what is quantum computing? It might be clear to you, most of the people, that something related to quantum mechanics, something related to computers. Let us have a close look. So today's computer represent information only in two binary digits or two states, 0 or 1. We also call them bits, and this can be actualized by switches that we call transistors, MOSFETs, others. And grouping these transistors, we can make gates, right? We can make gates for doing logical operations. But there is a issue. What is the issue? Issue is that if you think about that, to represent a letter, right, A, B, C, we need at least 1 byte of information, about 8 bits. So if it grows from letter to word to paragraphs, so you soon reach to 1000 kb or megabytes, right? And so it's not a future, right? And Morse gave a law that in our every 18 months we will have of transistors on a chip. But in last decade we have a steady growth in that, because we current silicon technology has already reached to nanoscale. And if you think about right? If you go more inside that, then you will reach to angstrom, right? And theoretically, the Bohr's radius of one single electron atom is of angstrom order. So you can probably think that we are reaching to quantum world where our classical principles don't take hold. So what quantum will bring to us, right? If you are familiar with young double slit experiment, yeah. So we have a particle can show both behaviors that we also call matter wave duality. So more the momentum it is, the de Broglie wavelength will reduce. So that's what we call a principal superposition, right? One quantum state can be in multiple states till it is not measured. Next is entanglement. So entanglement is something famously Einstein called spooky action at distance. Yeah, it is spooky because classical mechanics or electromagnetism follow localization, but quantum mechanics is non-local. So that's why entanglement. We will see some points more about entanglement. Then we have interference. As discussed, that matter have both wave and particle nature. So it interaction will be sometimes like wave. So we may have interference patterns. So this is an example that how we represent quantum states, and as they are binary, so we call them quantum bits or qubits as a short name. In the left side you can see this purple disk, right? This is called block sphere. Actually it is a sphere. We will discuss more about it. And this is a zero state. We will understand the representation what it means. And in the right side we have a quantum circuit, right? Unlike classical, in quantum mechanics, observable changes with measurement, right? So measurement is also an operator. We will discuss it in more detail in coming slides. So superposition, right? So whatever we do in quantum mechanics is in complex space, right? Complex vector space, also called Hilbert space, and we follow Dirac notation. This represent cat 0 and cat 1. And in the left side if you can see, this is called block sphere. And you probably understood so far, this is a complex space, so it follows complex geometry. Now one may question, right, why it is sphere, why it is not cuboid, right, why it is not something else. So for that, like if you aware that in quantum mechanics we follow polar notation, right, where radius shows proportional to the probability of that state, and the angle represent the phase. So if in complex number we have cis notation, so it closely works like that. So let us take an example. So it is a cat 0 and cat 1. So in a superposition state, we can represent A into cat 0 plus B into cat 1, which means that after measurement, there will be probability A modulo square to get cat 0 and B modulo square as cat 1, right? We will discuss that what is this measurement operator in detail. Next is gates. In the left side, you can see that we have classical gates, right, that are made of transistors, MOSFETs, right? And in the right side, we have a quantum gates, right? Hadamard gate, measurement gates. But like quantum mechanics follow principle of unitary. So these gates are reversible and are unitary. So uh, as these are reversible, right? So if I put even number of these gates, it will be identity, right? It will be neutralized. So let us take an example. This is an example of poly-X gate, commonly known as bit flip gate. Why? Because if you put cat 0 state, then it will change it to cat 1 state. And next is Hadamard gate, that basically used to change that distribution to equally likely, right? Like if you give it a 0 cat state, the probability of getting 0 and 1 will be equal, right? Now, interference, like as I stated, that we a matter have both uh, wave and particle nature. So we have interference. We one state can interfere to the other probability, right, and can change. So in the right side, we have an results of Grover's algorithm where we want to find 0 1 0 state out of these many states. So you can see how the amplitude grows, and we could find in a polynomial root and complexity, right? We have now entanglement, right? Entanglement is something a complex principle, or you can say a complex understanding, because if two qubits are closely connected, or we can say entangled, and like let me give you an example that why Einstein called it a spooky. If you have a two qubits, right, they are entangled. It doesn't matter if you put them in the end of universe, right? Separate them with the distance of universe. If one changes, then other will automatically changes, and which violates the spatial theory of relativity, that how information can transfer space more than speed of light. So that's why like Einstein and other researchers famous published EPR paradox. Yeah. So that's what entanglement is. In mathematical terms, if there is any mixed state that can't be factored, we call it entangled. Like in right side, you can see this first state cannot be entangled because we can extract cat 0 state, but others too we can't. That's why they are entangled. Yeah. So now comes measurement. That's very interesting. Classically, measurement doesn't play any role in the observable. What it means is that suppose a person is walking, right? It doesn't matter, right, if it has velocity v. It doesn't matter till you have a uniform frame of reference, right? Your frame of reference is not accelerating or deaccelerating. You will see that velocity v, right? But in quantum mechanics, it doesn't hold good. So while changing the measurement operators, you may have different outputs of same state. So that's something counterintuitive, and it you can like relate it to uncertainty principle, that if you can precisely measure the position of a particle, then there is a high uncertainty in the momentum of the particle. So that's intuition behind this measurement, right? It is a whole a deep study that measurement has a big concept in the quantum mechanics, if anyone way. So we saw that what is classical, what is quantum computing. Let us discuss with the problem, right? We have a caffeine structure, right? In the right side that we drink coffee, right? So we have caffeine structure. We want to understand that what is the ground state of this caffeine and how we can simulate this chemical reaction. So let us consider that how much space or how much processing we require to process that on classical computer. It is approximated that 10 raised to power 48 bits are required for a single caffeine molecule, right? So, out like if we talk about order, then it is 1 to 10% of total number of atoms in the earth. So you can understand that how many transistors you may require. One bit may have more than one transistor or one MOSFET. So you can understand that it is a huge number, right? And if we discuss same problem with quantum computers, we have 160 logical qubits only. Why? Why? Because we exploit principle of superposition. And if you have a calculator, a scientific calculator nearby you, then 160 represent 2 raised to power 160 quantum states at the same time, right? And in the right side, if most of you have recognized, this is our IBM research team that is looking for redesigning cryogenic freeze, right? Refrigerator. We will discuss that. Yeah. So like IBM, we at IBM making quantum computing using superconducting qubits, yeah, Josephson junctions. So we need temperature uh, below some millikelvins, right? If you people have seen quantum computer few years back, right, there was a big chandelier, there were lots of cables, but now you can see that it is not such big, and there is some boxes, right? So reason is that with changing time, technology has changed. Number of qubits on the circuits has increased, and it is found that there are noise from cosmic radiations also that change the results of quantum computers. And at 10 millikelvin, right, it is like for a understanding purpose, it is cooler than space, outer space. So at that temperature, coaxial cables become brittle. So we have now complex wiring that supports that, and we have these boxes to protect our qubit chip from outer radiations and phonons. So now we discussed that what is quantum mechanics, what are quantum computing, classical computing. So let us discuss that what kind of problem it will solve, right? So in theoretical computer science, we have concept of NP and P hard problems. P means polynomial hard problems and problems that are not polynomial hard problems in the complexity of time, right? So in that space, there are some problems that are polynomial complexity, P, and there are some problems that are NP hard, not polynomial problems. Quantum takes advantage and can solve most of the polynomial problems and can solve some of the hard problems, not all. So that we called quantum easy problems, right? That is called quantum easy problems. So that's what theoretically it means with the complexity theory. So now question arises that what are the practical problems, right? We can solve with quantum computer. So most of you understand with this helical structure protein folding problem, right? Protein folding problem is one of the toughest problem that today's supercomputer also could not perfectly solve that. Why it is complex is that proteins are very very reactive, or you can say very very volatile in the environments due to deuterion in the acid or base environment they changes, and they are the building blocks. Amino acids are the building blocks of life on earth. So it is a very complex problem as considered in mathematical or computer science to solve it. It is estimated, right? If we want to perfectly solve uh, protein folding problem, it will take 63 petabytes of memory. So for consideration, one petabyte of memory is equivalent to about thousands of terabytes. So you can understand what is the order of the storage we need. But with the quantum method, we can only solve this problem with 77 qubits and in 12 minutes. Yeah. So that's a big advantage that people are betting on. Other problems that IBM has currently collaborated with many industry leaders to solve some of the interesting problems. Yeah. On the left side, IBM has collaborated with BMW to to understand the lithium ion battery and electron charging, right? Concept, how we can do fast, how can we make better batteries. And another is airlines, like we need a lightweight material to fly. We need a aerodynamic material with that can fly easily. That's where we come. Next is drug discovery. We have collaborated with Cleveland and other hospitals to provide help and understand how we can do better vaccination or drug discovery using quantum algorithms. Next is communication sector. If you people are aware that post quantum cryptography, right? uh, America and America and other developed countries had already made a law that state-sponsored or essential all the government units should change their cryptography to post-quantum cryptography. They should prepare it, and IBM has published some of those algorithms and get recognized from NTA. And now we recently, if you are aware, that HSBC has published that with using quantum computers, there are more than 34%, right? 34%, a big number, than a classical technique advantage for trading. So that is a big fit that we using quantum computers we are have more advantage about 34% in finance world. Now, if you understand that unlike classical, the quantum talks about cat 0, cat 1 state, how we can model them, right? How we can model these problems to quantum computers. Quantum has advantage, no doubt, but quantum can play only to special structure of problems. Not all problems we can take quantum to exploit. So, what kind of problems, right? So we in if you are aware of, IBM is increasing a quantum utility scale. Like, it is not noise free quantum computer, or it is not fault tolerant, but it is using quantum computer at utility scale. What it means, we will see. So in 2023, right, IBM's most one of the best microprocessor quantum processor unit heroines are has showed that more than 5002 qubits has 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 given the results that in reasonable time and with less error. Likewise, as if you have seen the quantum utility roadmap at IBM, you can see that, right, we are heading in 2029. We have 100 million gates fault 100 million gates with reasonable error rates, right? We have recently we have published quantum LDPC and other algorithms for error mitigation and error correction, right? So what do you mean by quantum advantage? That most of the people like talk publish that we reach to the quantum advantage. What it means, it means that whatever the quantum computer is giving us results, right, they are correct and that are logical. So it is about trust, right? It is about trust. And next is advantage compared to classical. If we advantage can be of time, it may take less time, it may take less resources to get same result, right, as compared to classical. This is like about benchmarking, how you can benchmark a quantum processing unit, and how you can say that, okay, we, as compared to the classical methods, we have some advantage in quantum mechanics. This is what it is. So most of you, right, most of you when visited from one place to another take different types of modes, right? Someone take cab first, then airport, airlines, then again cab, and then your destination. It's something holds good in quantum computing also. Alone quantum computers, alone classical computers can't make things well, right? So there are some sets of algorithms which we call variational quantum algorithms that take advantage of processes that can be cheaper on HPCs, high performance computing, and can be expensive at quantum computer, like optimization, you can say. And we take advantage of quantum computers to have exploit superposition, entanglement, and other. And see, if you saw our previous slides, we talked about quantum easy problems, correct? At IBM, we thought that one beautiful idea and at right time can make things working. There are lots of problems that are solvable with quantum computers. There are some problems that are impossible with classical computers. There are some problems that are impossible for Grover algorithm. We need a full fault tolerant quantum computer, right? Which can do arithmetic operations that are easy problems. So we can't wait to the make a fault tolerant computer to have utility and take to solve a problem. So that's where we come to the sweet spot using NISC, right? Nearest era quantum computers to have solve practical problems and get advantage. So as we discuss real-time problems that we are using quantum computers to solve, they are classified into mainly four classes. One is chemistry and materials, right? We have problems that of ground state, how the molecular ground state is, what is a chemical reaction in drug discovery, optimization and search, max cut problem, QAO, quantum approximate optimization algorithm, such kind of algorithms. Machine learning and AI, we have algorithms for quantum machine learning that like basically as we saw in superposition, we have lots of space. So we can use that, leverage that to map few feature maps. Like if people are aware of state vector machines, they were earlier to the neural networks. We can use quantum computers, right, to calculate inner products or those feature space easily, right, without taking more qubits or more bits. Numerical simulations, we have Monte Carlo, other kind of simulation that we can take on quantum and take advantage of. So here, like we like Qiskit, we encourage Qiskit plus IBM quantum processor. We have utility scale of work, right? So Qiskit, I will discuss more about that. Qiskit is one of the top and fastest quantum software development kit available to the community and is open source. So we to as in noise era, we need a quantum computer that is performant and easy to use, sticking to Occam's principle that keep it simple. So this block diagram is of IBM quantum platform. Like when I started quantum computing, there were not many things, right? There were quantum computer, quantum processing units, HPCs, right? There were quantum Qiskit SDK. Most of these things with time has added, like Qiskit runtime, Qiskit serverless, Qiskit HPCs, integrations. So let us go one by one. Here, like quantum computer in your lab, right? Basically in the superconducting quantum computer architecture, we use microwaves to change the state, to apply the gates, to understand the results. So here is your quantum computers and here is your quantum chip. Qiskit runtime basically is used to queue and manage the jobs, right? There can be lots of jobs on your computer cloud that needs to be simulated on the same chip. So Qiskit runtime optimize that and reduce your waiting time. We need HPCs to figure out the microwave, analyze the microwave, or you can say we have controllers, right? That are HPCs. Then we have Qiskit serverless, Qiskit HPC integration, right? We Qiskit sports integration with other high performing computing resources to reduce the time. Then we have Qiskit SDK, Qiskit software development kit, Qiskit add-ons, Qiskit transpiler service. Basically, that is how, like when you write a code you post to the quantum computer. So Qiskit and OpenQASM do the things in the backend. In last year we launched Qiskit code assistant also in the quantum developer conference. So this is where that you can do normal quantum computing or quantum circuits. Now comes quantum function catalog. So we have some specific problems, like we have a chemistry simulation problems, we have problems like machine learning problems. So we have introduced circuit functions, and application functions. And you will be happy to know that some of the functions, application functions, are contributed by the industry, quantum startups, and others to enhance and use their specialization to solve problems on quantum computer in more easier frame, right? So what is Qiskit, right? In 2017, IBM launched Qiskit, right? Make it open source quantum development software development kit to public, and also uh, make quantum computer on cloud public to everyone. So everyone can just go search for ibm.quantum, and you can connect to the quantum computer, and you can do entanglement, superposition, whatever, right? So here is a slide that I want to show, that unitary fund, right? If you know, unitary fund does annual survey about quantum computing development, quantum computing programming language, SDKs. So in today there are 10 plus hardware providers like IBM Quantum, IQM, Azure Quantum, Allison Bob, INQ, Amazon Bracket, Superstack, Quantinuum, Rigetti, right? Out of that, 74%, yeah, 74% people has recommended and prefer that they use Qiskit software development kit. And you will happy to know that most of the contribution on the Qiskit, 75% is contributed by the community. We have a very vibrant and engaging, interacting community. And there are more than 5,185 projects that use Qiskit, that are dependent on Qiskit. So there is this time comparison, right, as compared to other quantum software development kit. IBM Qiskit has only taken 49 minutes as compared to TCAT approximate 27 hours. You can see that we have a lot of 100% or more than that kind of order. Let us take time to speed and build of that circuit. Like you put a code there, right? In the back end, the quantum computers quantum transpiler, right? That map those quantum circuits to actual qubits. If that is not optimized, your circuit may break or it may take time. As compared to the available quantum software development kit, our Qiskit has about more than two times of speed advantage. So now let us talk about gates. So like you put H gate, sometimes what happens, qubits on hardware are not connected. So you need multiple C nodes or cross gates to transfer the information from one qubit to another qubit channel to another qubit channel. So quality. So we at like as compared to other available quantum transpiler, you can say, or other quantum software development kit, we don't overhead with the gates, right? It reduces gate and reduces noise. Like if you have more operators, more gates, you may susceptible to more noise. So we have only one X, that is a huge advantage. Now you will ask, okay, we how we can use quantum computer, how I can model quantum computer problems. So for that, I want to tell you that it is not new. It is something that you used to do. Like in classical, what do? You have a problem, you just take and map it to the your classical gates, or you can say variables, right? then you optimize the code, and then you execute. After execution, whatever you have the results, you analyze that. It is similar in quantum also. Whatever you have a problem, you make quantum circuit for that, right? Optimize, you need not to optimize. When you compile it, automatically transpiler optimize, like optimize on route, like as I said, that in real quantum hardware qubits are not connected or maybe far away. So you, if you want to entangle them, right, you need more gates, and you have to make a route and optimize that. And like so, for historic reasons, transpilers, we use term transpilers instead of compilers, but they make similar sense. Like if you are from a classical computing perspective, so transpilers means compilers. Then you execute, right? You have multiple jobs, you have a big circuit to simulate. It may take 5 minutes, or may take 10 hours or 10 days. Qiskit runtime here is a great advantage. It will break that job in multiple batches and optimize the results. And then we have result processing. Now you got a result, right? You have this qubit of this amplitude, this qubit of this amplitude. Now you want to analyze it, you now want to visualize it. So we, in real library, Qiskit library, we have Qiskit circuit library that we have all the tools to make circuit. Then we have transpiler in the backend, OpenQuasm or other. We have transpiler that will route your quantum circuit into actual hardware in optimized way. Then we have primitives, right? We have primitives to share the workload, right? You have a big circuit, how you can simulate, how you can simulate primitive to help you out. Then we have a data visualization or expectation value visualization library, quantity visualization. That is also part of Qiskit. You can use that and you can make block spheres, state vectors, bar graphs, heat maps, whatever you like. So now with Qiskit add-ons, right? We have Qiskit add-ons also. You, if you want more than Qiskit circuit library, we have AQS. We support AQC tensor, we support MPF, we support OBP, right? OBP, operator back propagation, circuit cutting. We have a sample-based quantum diagonalization, and much more. You can leverage that to make more advanced quantum circuits. So we can say that with quantum add-ons, right? We have Qiskit add-ons, Qiskit functions, and Qiskit and quantum processor units. We can have some utility scale work that we, one of them that we have discussed with HSBC, right? We have a 34% more advantage than the traditional or classical, uh, yeah, traditional and classical methods. So let us take like let me go through one Qiskit 101 notebook. Just right, you can try it your right. Let me share my screen. So yeah, so here it is. Yeah. So first of all, to use if you want to run quantum program in real hardware, you need a quantum platform credentials, right? First of all, you need to
Uh,
install Qiskit. Yeah,
Raghav,
yeah.
I believe you've used this link or you've gone to a notebook, so you have to share that, right? I believe
Okay,
that
okay.
will be
Just a
shared
minute.
here.
Yeah. Thanks for. Yeah. Mm, yeah. I think it works now. Yep.
Mm, it's getting added, but okay, got it. Now it
Yeah.
should work. Yes, great.
Yeah. So first of all, as I said, first of all, you need to install Qiskit at your local machine. So you need to make a environment. It is always recommended while installing any library. You need to make environment, right? Python environment, so that there should be no dependency conflict. So you can install Qiskit visualization for visualizing that we in recent releases we have changed from, like, we have another library in the Qiskit that helps in better visualization of quantum results. Then we have Qiskit IBM runtime that I discussed, that if you want to break a big circuit into multiple jobs, right, then we have Qiskit Air for applications. We install the Qiskit, then we import, and to simulate, right, on real quantum computer, you need to go visit to IBM quantum platform, right, and you need to just sign in. You will get the credential. This is the only place that I will discuss later on. This is a single place you can get everything. You can get documentation, you can learning, you can get functions, whatever you want. If you have any problem, just search here, you will get the answer. Yeah, this is a book. You should bookmark this if you are learning Qiskit or quantum computing. It has everything, every detail. Then after getting a IBM Quantum platform, you will see such a page, and you can create an instance, and you can get API keys and CRN number that identifies your credential, and you can load that and log into your quantum instance. Right. After saving your credential, you import necessary libraries according to your needs, and then you can use, like, here we are making a state vector 0 or 1 and plotting that in the q sphere, right. Likewise, like, we have zero cat state using Hadamard. We can have had a matter of 50-50 state, right? We have bit flip state, another state. Likewise, here is a notation. It is like quite clear, but X represent poly X gate and 0 represent the qubit, right? Which qubit you want to apply. A Y represent poly Y gate, Z represent poly Z or phase flip gate, right? We have a Hadamard gate for superposition. Then we have other phase rotation gates, Clifford gates, right? So this, you can try it your end, that you can. And there is multi quantum qubit gates, right? Multi quantum qubit gates has one classical, sorry, yeah. So multi-quantum computing gates has one argument for each bit, that is called quantum bits, right? If you want, like, here, basically you are in the control gates, you have one qubits that will control to the other qubits, right? So first argument represent the qubit that is controlling, and second represent what to be controlled, target qubit, right? Control qubit and the target qubit. There are swap gates, right? These are the, like, basic introduction about gates. Now you want to you have map the program correct. Optimization will be done at transpiler scale. You need not to do anything. You need to execute it, and you, in the post process, you will get the result. Optimizer, you can, like, you can use your own optimizers. Like, we have a multiple pass manager, right? You can give a optimize level, you can give IBM backend, right? Then you can optimize it. You can put measure all for measure operation. Then you put a job and you get the job ID. After getting the job, you retrieve the results, and you can there is a So it's all. So hopefully you people will enjoy and while using that. Yeah. So let's go back to our slide. Yeah, Shahir, is my PPT is visible?
Hello.
Yeah,
Okay. Yeah. The Jupyter notebook has been gone from the stream.
yeah. So is my PPT is visible?
Yeah, I have added
Yeah,
that.
I think. Yeah, I think. Yeah. Thanks. So this is where what walkthrough of a quantum Qiskit 101 notebook. Now, what are the next steps like? Like you are eager. I guess most of you are eager to learn more. That okay, we understand that what is quantum computer. We understand quantum mechanics somewhat. Yeah, we understand it is Qiskit. Yeah, we can do it locally. We can connect quantum computer. What else we can do? Right? What else? You have lots of scope. So we have a dedicated platform, what we call IBM Quantum Learning, that I showed. Right, you go to quantum.cloud.ibm, you have IBM Quantum Learning platform. There you can get specially curated courses. Right, you have multiple courses for everyone and self-paced. You some of certificate you after completion of some of the courses you may get badges. Right, you can get a digital badge certifications, and these are curated by leading quantum experts from the industry. Right, this is how IBM Quantum Learning platform looks like. Then we have Qiskit Advocate program, Qiskit Global Summer School, and dedicated YouTube channel Qiskit for releasing and have a demo of new quantum releases. We have Qiskit Developer Certification also. Let us discuss. Qiskit Global Summer School is one of the largest educational event like annually that IBM conducts. Recently, we have a close quantum Qiskit Global Summer School 2025 with more than 6,000, right? More than 6,000 people attended that. Every year we come with new themes. Uh, and it is open for all. If you don't know quantum computer, no worries. If you don't know quantum mechanics, no worries. We support that. It is 2 week event. Experts from the industry help you them. They are give lectures from basics, and you will learn a lot. And every year there is a different theme, right? You will enjoy that. Qiskit Fall Fest. Qiskit Fall Fest is like this event that school or college advocates organize quantum computing events at their campus. IBM supports that. They can ask for IBM for any special experts or speakers. And we have our quantum summer internship program also. We will like to tell you that quantum summer internship program is open for 2026 internship. Please check it out if you want to have a quantum summer internship and see your eligibility. Hopefully some of you will meet me. Yeah. And we have a Qiskit developer certification. Yeah, this is a professional certification that certifies that the holder have quantum computer researcher knowledge, and it is well versed with both Qiskit and quantum computing. So if you want to show it to any industry, you may take a chance. Yeah, it is great way to learn. Then Qiskit Advocate Program. Qiskit Advocate Program is a global cohort where our community, Qiskit community members, volunteer to do mentorship, networking, and events, and also get recognized from community. We can connect with the like-minded people. We help people to grow in quantum computing space. We help them solving their problems. Now, Qiskit Advocate program is also open, right? After years break, Qiskit Advocate program is back. So you can, what advantage Qiskit Advocate program will provide? You access to the Qiskit releases. You can leverage. Uh, you can use IBM Quantum Cloud features before it going to public. You have a more uh, cloud credentials, right? You have access to Qiskit education and events, and you can also meet experts, peers, and learn and do mentorship, right? This year, unlike last time, we have different tires, right? Qiskit Advocate, but don't worry. If you contribute to Qiskit, if you connect with the Qiskit events, it's all cake, right? And here in the right side, you can scan and register for the Qiskit Advocate event. It is open and year long, right? So that's all, and hopefully it's the end of slide, and I am open for the questions. So people keep learning, and yeah, sorry, yeah, we can continue.
Great, great. Okay, thank you so much for the sessions. I believe we have two questions till now, and folks, you have this. You can just ask your questions now. Okay, okay. First of all, adding this one, I believe he asked, "Can you describe the application where quantum computing may come handy with mathematical and logical explanations?"
Okay, it is a good question. I will suggest you should see quantum cryptography, right? Basically, if you see, when we talk about quantum computers, it's all about mathematics, right? We see cat notations, we see unitaries, we have Hamiltonians, so it's all sorts of mathematics. But if you are specific to question that yeah, we want any application in mathematics, right? So in that case, I will suggest you should see cryptography. Cryptography, like Shor algorithm, basically that is a number theory problem that quantum computer can solve in the less time to as a classical computer. Hopefully that answers you.
I hope that answers this question as well. If the question is not answered, or if you haven't got the answer as you require, feel free to add another question as well. Okay, so another question is from Imtiaz. That is, what is the future of quantum computing in medical health sector with advancing AI in this sector? Can you just give a visual for this, please?
Okay,
So,
it's a nice question. So, I will rephrase this question, right, to make it more deeper understanding. Like, people may sometimes compare, okay, this is machine learning, this is high performing computers, this is quantum computers. So, what is advantage, right? So, as I discussed, right, we have specific sphere, right? We have quantum easy problems. Might or might not be that are machine learning easy problems, right? That can be or cannot be. And if your question is specific to the medical health sector, right? The medical health sectors, we have a like quantum tomography. If quantum image processing, if you go in the radiology side, right, MRIs and other scans, we have quantum tomography. And in machine learning, we have machine learning, convolutional neural networks, and other models that are taking leap. But I will suggest, instead of comparing both, they have both advantage and disadvantage. Yeah, quantum computers have medical health applications, and IBM has collaborated with the Cleveland Hospital for doing research in drug discovery, vaccination design. You can check that out, right? So there are applications, right?
yeah. Okay. Another question from this was, can you share this PPT? I believe this might
Ye-
be.
Yeah, after the event, I will soon as Monday I can share it. Yeah.
Okay, great. That would be great. Okay, so you have shown like I was watching these slides. So yeah, according to uh, the research uh, conducted like within September 2024, there was lots of stats showing like how Qiskit has advantage over other things. So now the question to you, obviously, you have also mentioned about the learning platforms from IBM Quantum, how from where they can learn. Also talking about this quantum computing, obviously Qiskit, and how they can use the real world quantum computers using IBM Quantum Cloud, right? Great. Now, my question from you, sorry, to you is basically, as a beginner, complete beginner, how should one start actually learning quantum computing? Because this question comes up like this is like there are a lot of folks in our country who are doing bachelors in computer science. There's some folks who are doing bachelors in physics, but quantum computing is something which has, I believe, two things in common, right? So from
Yeah,
where they should start?
yeah, Shahid. Very good question. Thanks for asking. So, like, not like other communities, like IBM Quantum, or you can say Qiskit, or you can say quantum computing as a whole, is very inclusive community. It doesn't matter if you have an electrical background, if it is a physics background, it is computer science background, or mathematics background. It is open for all. It has something to do with everyone, right? Let us like take an example, right? If you want, like, how cryogenics works, right? You have lots of scope in making a cryogenic refrigerator, redesigning for quantum computers. If you have knowledge in physics, right, you can have a lot of applications where you need to make Hamiltonians, right? Or you have chemistry knowledge, you have lots of scope in quantum chemistry, like you have knowledge of molecules, right? You have a lots of scope. But now you are asking is how you should start, right? So it depends. If you are in high schooler, right, you don't know that what is quantum mechanics, you don't know that what is computer even, right? You don't know gates. No worries, there are resources available on IBM Quantum Learning. You have resources open apart from IBM that simplifies it. One of that I will suggest is Coding School, qubit by qubit, that is specifically designed courses that start from scratch, where people don't know, okay, what is vector, how will I represent, and goes till Strauss or Grover algorithms, right? You can take that. And for college graduates, right, start contributing, start engaging, like meet peoples that like you, like me, meet peoples, think about them, ask them, okay, I have buddy, I have this much knowledge, how can I utilize this? IBM has made quantum computing completely open source. Like mostly things are available. You can, if like you are people that learn from videos, we have YouTube channel. People who want to read, we have documentation. People who want to take certification, we have IBM Quantum Learning. And if you want to contribute, we are open. Qiskit is open source. Just check out GitHub repository, pick any issue, start contributing. We are open. Yeah. I think hopefully it answers your questions.
Yes, yes. Like especially talking about the Kiss Kids YouTube channel, that is very handy. The explanations are
Yeah.
very good. Yeah, I believe. Yeah, this is how we can grow the community. Okay, I can't see any more questions here. So if there are no questions, I believe we can end our session. So yeah, thank you so much, Raghav. It was a detailed session. You started with the principles of quantum computing, and then you have shown us a notebook. But I believe folks would love to actually run the notebook if they can. So that would be great if that notebook is also shared with us.
Yeah.
So yeah, after if this slide is shared, I believe they can get it through the
Yeah.
note.
Yeah. Share in the next week. So I will share the all the material with you.
Mm-hmm.
Hopefully, you enjoyed the session, and it is a pleasure to meet all of you remotely. So, but if time allows, one day we will meet physically also in person. And
Yeah.
happy quantum learning. Yeah, thanks for having me. Yeah,
Yeah. Thank you so much, Raghav. So yeah, see you then. Bye.
yeah. Bye, bye. So.
Uh, okay, so that was a session, and it was mostly on quantum computing, right? So we have another in-person session, in-person meetup, basically you can call it. So it's going to be held in November 15th at Brack University, and we will have all the Bangladeshi folks, especially from IBM, Duke University, and other universities who are doing PhDs there. They will be sharing some resources, some insights. Even they will show you how quantum computer is working. So I hope you have registered for that event. And if you have any questions, come join us in that event, and we can have a discussion and meet up on this. Okay, thank you so much. It might be overwhelming for you. I do understand. It was also overwhelming for me at the start, but it's a process. So let's go with it. And if you have any questions, feel free to add it here. I will refer it to Raghav. Or if you have any questions in person, meet us in at Brack University November 15th. So thank you so much, and hope to see you.